Hi folks, how you doing today? We shall be considering a study on geometry. Geometry is a very important branch of mathematics. It's a very wide branch and it has many applications. All right, so we want to look at a study on geometry, and it is important to put down the important terms that will enable you to grapple with the study of geometry. In this video, I shall be giving a detailed explanation on what is geometry and on some terminologies that are used in geometry. So before we continue this adventure, I would like to inform you that I render an online math tutoring service. So if you're interested in an online math tutoring service, be very free to get across to me. All right, be very free to get across to me so that we can make organization of how the class will be. In such a class, you have the liberty to ask me questions in real life time. If you are not clear with a particular concept, you have the liberty and freedom to ask me directly, and I'll do my possible best to bring the correct idea to you. All right, so be very free to get across to me if you are in need of such a service. As an addendum, I also render assistance. I also assist in providing solutions to assignments and tests, and also in projects and research work. So be very free to get across to me if you are in need of any of these services. All right. Please do me the favor to subscribe, like, and share the video if you gain any value from it. You do me that favor to subscribe so that whenever we post other fascinating math video like this, you will get notified. So also share and comment so that my video will be counted worthy to be recommended for other audience. So thank you very much as you do that. Now let's look at what is geometry. When we say geometry, what does it mean? Definition over here. Look at the definition of geometry. Let me illustrate with this. Let me use this to illustrate now. Can you see this? This is the definition of geometry. Now here it says geometry is the study of the properties of shapes. So geometry is a study of the properties of shape. Someone who studies geometry is called a geometer. You had not added to it in the write-up. Somebody that is studying geometry is called a geometer. Now from this definition, we observe the following terms. The first one here is properties. The second is shapes. Now let's elaborate on the first. When we say properties, property is meant the math features, the mathematical features or characteristics or behavior derivable from shape. Those properties, those features, those characteristics, those mathematical features, those mathematical behavior that you get from shapes, we call them properties. All right. So what we are studying in geometry is the mathematical features of shapes, such as angles, lengths, and so on. All right. So when we do that, what you are involved in is called geometry. Now, when we say shape, this word shape is a very vast word. There are different kinds of shape. We have the two-dimensional shapes. But we have the one-dimensional shape, which is a line, and we have the two-dimensional shapes. And example of two-dimensional shapes with the rectangle is a two-dimensional shape. They are otherwise called plane shape. Why are they called plane shape? Because they can be drawn on the plane. When we say plane, a plane can be regarded as any flat surface. All right, you can take a plane as any flat surface. So any shape you draw on that flat surface is regarded as a plane shape. So that means a triangle, circle, rectangle, and so on and so forth, they are all plane shapes. So when we say geometry is the study of the properties of shapes, the shapes here can be plane shape. Then we also have the solid shape, such as the keyboard, the pyramid, the cylinder, and so on. All these are solid shapes, or they are otherwise called the three-dimensional shapes. So, but in this course, we shall restrict our study to plane geometry. we shall not be going to the study of a 3D geometry. All right, so we shall restrict our study to plane geometry. Now, in so experimental geometry, experimental, please take note, this is not, I think there's a mistake here. Let me remove it. This is the point I'm talking about. This, let me illustrate with this. Can you see this? Look at this. Is it this? No, not this line. Look at it here. Can you see? I said in experimental or practical. I mean practical, not theoretical. All right. This word theoretical or not to be as practical. So in experimental geometry or practical geometry, these properties, you know what I said earlier on, that geometry is a study of the properties of shapes, and the shapes can be plane shape or solid shape. They were narrowing the study to plane shapes. So in other words, we are looking at plane geometry. So plane geometry is a study of the properties of plane shapes. All right. So in experimental or practical geometry, these properties are studied and proved by the method of drawing and measurements. So you use your mathematical instruments such as your protractor, your set square. You use them to draw shapes and use them to measure angles and lengths. All right, use this instrument to measure angle and length. For example, we can draw a triangle and measure the angles, the interior angles in the triangle, and when we measure them, we can add up, and when we do that, we discover that the sum of the interior angles is 180. That is true for that particular triangle we drew. Now, we cannot establish that property is true for the general triangle. When we say general triangle, there are billions, infinitely many triangles. So it is not practicable to use this method of drawing and measurement to prove that the same property, that is the sum of the interior angles in the triangle is 180. We cannot use the method of drawing and measurement to establish that property is true in general, that is when the triangles are infinitely many. That would be very laborious. In fact, it's not really practically possible. So because of that reason, the empirical or practical geometry has a limitation. All right, so other kind of geometry have to be adopted, such as the theoretical or formal geometry. Now look at over here. I said, however, this method does not give a sufficient proof that these properties are generally true. All right, this line, I'm talking about this line. However, this method does, please take note of it, does, that is not, it is a mistake, it's an oversight. This method does not give a sufficient proof that these properties are generally true. So because of that reason, another sophisticated geometry has to be invented, which is a logical geometry, and it's called formal or theoretical geometry. Now, in formal or theoretical geometry, these properties are proved by a method of reasoning and arguments. So instead of using drawing, measurements and drawing, we don't do that any longer. Rather, we use a logical approach to establish that the properties are true in general. That is, when the shapes are considered infinitely many. You know, in geometry, we don't only deal with triangle. I only give triangle as an example. There are many other shapes we study, properties of other shapes. And the property can be related to angles, to lengths, to areas, to volumes, and so on like that. Now, when we speak of triangle, for instance, we speak of it as in general, all right? That is, when the triangles are considered infinitely many. So we want to establish that the fact or the claim that the sum of the interior angles in a triangle is 180. We want to prove that is generally true, that this is true for all triangle, which the method of measurement and drawing cannot establish. That is, empirical geometry cannot establish that. It is only formal geometry that will do that. So let us explain now the properties of shapes. Don't forget, I said geometry is the study of the properties of shape. These properties can manifest themselves in various forms. There are various forms in which this property can present themselves. Now, some of these forms are given here, hence with the subheading, explaining some forms of properties. The properties can manifest themselves in some form. The first form here is they can manifest as definition. So when you are reading through geometry and you see the right definition, they are defining a property for you. That is also a property. So the property can manifest or can present itself in the form of a definition. What is a definition? I said this is a statement about the main properties of a situation. When I mean situation, I'm not only speaking of geometry, it can be any other aspect of mathematics. All right. This is a statement about the main properties of a situation. Now, that statement about the main properties, we can call that a definition. Right? It's telling you what is obtained. For example, we can make this statement. This statement, a parallelogram is a quadrilateral with two pairs of opposite parallel sides. That is a definition. You are trying to define a parallelogram by the property it has, that it has two pairs of opposite parallel sides. That is the property. So because a parallelogram has this property, it can therefore be defined by using this property. All right. So the statement that a parallelogram is a quadrilateral with two pairs of opposite parallel sides can be regarded as a definition. Can you see that? So that is an example of a definition. Number two way the properties can present themselves. Please don't forget the definition of geometry. Geometry is the study of the properties of shape. Now, another way the properties can present itself is in the form of axiom. Now, what is an axiom? Axiom is a statement of assumption about a situation, and as such, it is not subjected to a proof. All right. So when we say axiom is a statement of assumption. You assume an idea, you assume a fact to be basic. So such an assumed property is called an axiom. So axiom is a statement of assumption about a situation, and as such, because it's an assumption, it is not subjected to proof. So there's no need to prove an axiom. We don't prove an axiom. It is a property that is considered as basic. So axiom may be self-evident or not. That is, it may be clear that the property, the property may be obvious. It may be obvious to you that it does not require a proof. That is, it's too basic. But some other time, it may not be self-evident. But all the same, it is an assumption that needs to be taken as true, that from which we establish other important facts. All right. So axiom is a statement of assumption about a situation, and as such, it is not subjected to proof. For instance, if we regard the sum of adjacent angles on a straight line as an axiom, then we need not prove it. That is very correct. If we assume that the sum of adjacent angles, which I will explain later, the term adjacent angles, I will explain it later, because every terminology here, you need to understand every terminology in order for you to grapple with the study of geometry. Otherwise, it will be very difficult for you it will be difficult and boring. But when you get every term, what they mean, the definition of every term, it will be very easy to study geometry, and geometry will become very interesting. All right. Please don't forget, if you draw any value from this video, do me the favor to like, share, comment, and also subscribe to be notified when other fascinating videos are uploaded. Now, we said that, for instance, if we regard the sum of adjacent angles on a straight line as an axiom, then we need not prove it. That is true. But rather, by that assumption, prove certain other basic properties called theorems. So theorems are also basic properties, but theorems can be proved. What is the difference between a theorem and an axiom? An axiom cannot be proved. It's not subjected to a proof. All right, it's an assumption that needs to be taken. But a theorem is subjected to a proof. Now let's look at the definition of a theorem. What is a theorem? A theorem is an implication. All right, a theorem is an implication. Now, a theorem has an antecedent, or you call it hypothesis, and a conclusion. So you can say an implication is a statement that consists of an antecedent and a conclusion. So such a statement is called a theorem. All right, but sometimes theorem does not present itself. Before that, let's look at this other aspect. You can call the conclusion a consequence. It's still the same thing. So a theorem is an implication in summary. Now the antecedent is the axiom upon which the conclusion is based. Yes, the antecedent is the axiom upon which the conclusion is based. That is what we are saying here, in effect, that in a theorem there are certain assumptions that will be given to you, which may be self-evident or not, but it's an assumption. So in a theorem there are certain assumptions, and by those assumptions you have to establish the conclusion that the conclusion is true. All right. So hence I said the antecedent is, or you can call it hypothesis, is the axiom upon which the conclusion is based. All right. For instance, if ... that is, any expression can be there. If that if part there is called the antecedent. Let's say if he come today, that if he come today is the antecedent. Then he will not go tomorrow. That he will not go tomorrow is a conclusion or consequence. All right. So that ... can be any expression, as I said. So if that is the antecedent, or you call it the hypothesis, then we call that the conclusion. All right, is an implication. So if ... then ... is an example of an implication, and this is how most theorems present themselves. Sometimes a theorem may not be given in the if and then formats. All right, sometimes you will not see a theorem be given in this format, as that is if ... then ... You will not see a theorem occurring in that format. Rather, you will see it in the ordinary form. For example, look at, I give an example here. Example: the sum of the interior angles in a triangle is 2 right angles. You see that this statement here does not present in the if then format. All right, rather it presents itself in the ordinary form. Now if we want to translate this into the if then format, it will be if ABC is a triangle, then the sum of the interior angle is 2 right angles. That is another way we can present this. The sum of the interior angles in a triangle is 2 right angles. So it can be translated in the if then format as if ABC is a triangle, then the sum of the interior angles is 2 right angles. So this is one way a theorem can present itself. So, but most of the time you will see it in this ordinary form. That is, I mean this form. Let me illustrate now. Can you see this over here? I mean this form. Most of the time, a theorem will present itself in this form and not in the if and then format. But it's the same thing. You can convert from one form into another form and vice versa. All right. Now, a theorem is always proved by a reasoned argument. That's what you should observe. You can always prove a theorem. So we'll be carrying out proof of certain theorem. Don't forget, theorem is just a form. The properties of shape can present itself, or their self rather. I said geometry is a study of the properties of. You should not forget that definition. All right, it's from that definition we get all this we are atomizing here. So let's look at another way the properties can present themselves. Lemma. It can present itself as a lemma. Now, what is a lemma? A lemma is an auxiliary theorem. That is an helping theorem. A lemma is an auxiliary theorem. Its main aim is to aid in the proof of a given theorem. Is to assist in the proof of a given theorem. That is to make the proof of a given theorem to be possible. Sometimes the proof of a given theorem will not be possible unless there's another property, another statement of facts called lemma. And that is the duty of a lemma, is to enable the proof of a given theorem. All right, so we call that kind of statement or property a lemma. Then number 5, we have what is called the corollary. The properties can also present themselves in the form of a corollary. What is a corollary? This is a direct consequence of a theorem. Now, because a theorem exists, consequently, a property will also exist along, just as a shark and a remora are very close together. Because shark exists, you see remora alongside. The same way, sometimes when a theorem exists, there will be a kind of branching out of the theorem, a direct branching, and the name of that branching is called a corollary. All right, it's called a corollary. So a corollary is a direct consequence of a theorem. It is an offshoot of a theorem. You can call it like, you can say it like that. All right. So please make sure you take your time to go through this video so you can understand these terminologies, because we shall encounter them in the course of this study. Now we'll go over to plane geometry. Don't forget, I told you that when we say shape, there are two kinds of shape. We have the plane shape, we have the solid shape, or you call it the two-dimensional shape or the three-dimensional shape. But geometry is the study of the properties of shape. It can be plane, it can be solid. All right. But we are narrowing our study, as I said earlier on, to plane geometry. Now, what is plane geometry? Plane geometry is the study of the properties of plane shapes. All right. Now, plane shapes are shapes that are drawn on the plane. I said that before. A plane may be regarded as a flat surface. Now, let's look at the angle. What is an angle? Now, given a fixed direction, that is, given a fixed line, a fixed direction, an angle is the measure of rotation of a straight line from the direction in either clockwise sense or anti-clockwise sense. So if you look here in figure 1, look at figure 1, you see that there is a direction OB, that is a fixed direction. Then a rotation from it, from line OB to line OA, describe an angle. All right. So because of the rotation from from the direction OB to OA, there is an amount of that rotation. That the amount of measure of rotation is called the angle, and it can be anti-clockwise, as shown in the first part. Look at it over here. I mean this part, all right, as shown here. That is, in this case, we have an anti-clockwise measure. While in this case over here, we have the clockwise measure. All right. So, but it's a rotation from a fixed direction to either the anti-clockwise sense, or clockwise sense. So that is an angle. Now, the side OA and OB are called the sides of the angle. Sides, S-I-D-E-S, sides of the angle. All right. So an angle has sides. All right. In this case, we have it as OA and OB. That is in figure 1. Now the next we want to define what is known as adjacent angles. What do we mean by adjacent angle? When do we say angles are adjacent? Now take note, many people do not know this term. When they say adjacent angles, they don't know what it means. So adjacent angles that are next to each other, we call them adjacent angles. All right. Adjacent angles are angles that are next to each other and have the same vertex. The plural of vertex is vertices. Now, in figure 1, the point O is called a vertex. Can you see that? Look at it over here. This point O here is called a vertex. So, if angles, so the term adjacent is not a monopolized word. It's to be used for more than one angles. You cannot use adjacent for only one angles. It must be 2 and above. All right. So, adjacent angles are angles that are next to each other and have the same or a common vertex point. Example, look at figure 2 here. In figure 2 here, you see that we have various angles. We have angle X degrees, angle Y degrees, angle Z degrees. You see they are next to each other and they have a common meeting point. Because of that reason, we call them adjacent angles. All right. Now, when naming angles, we name angles by the lettering. Now, for example, angle X degrees, the vertex of that angle is O. All right, angle Y degrees, the vertex is also O. Similarly for Z, the vertex is O. Now, when naming angle with letters of the alphabet, we ensure that the vertex is at the middle in the order of naming. Now, when naming, for example, I want to name angle S, I can name angle S as angle AOB. Don't forget the length OA is called the side of angle X, while the length OB is called the second side of angle X. All right. Now, when we want to name angle by using the letters of the alphabet, we ensure that the vertex is at the middle in the order of naming. For example, look here. Can you see this? Look at this. It's either you name it angle AOB or you can also name it as angle BOA, provided the vertex is at the middle and the sides are involved in the naming. Because in this notation, you see that AO is the first side of the angle, while BO is the second side of the angle, and O is the vertex. So when naming angle, ensure that the sides are involved in that particular angle you name, and also the vertex of the angle is at the middle, at the center. It is a necessity when you are using letters of the alphabet to name angles. All right, so that should be taken into consideration. Now we're done with that one. Let's go to you can read through the notes. Now let's look at parallel lines. What are parallel lines? Parallel lines are lines that cannot intersect when extended in either directions. As simple as these terminologies, they have a great consequence on our future work. All right. In subsequent work we'll look at, you will see that these little things I'm defining to you now have a great consequence in the existence of other things we'll consider later. So it's very important to get this foundation very clear so that you'll be able to grapple through with future work. So parallel lines are lines that cannot intersect when extended in either directions. All right. Arrowheads are usually used to indicate that lines are parallel. Example of arrowheads is this arrow you see here. Can you see that? Look at it here. That is what you also see in this other part. So when these symbols are drawn on lines, it means that the lines are parallel. Once again, the term parallel cannot be used for only one line, just as the term adjacent cannot be used for only one angle. The same way, the term parallel cannot be used for only one line. It must be two and above. All right. So lines are parallel if they cannot intersect when they are extended in either direction, as shown in the figures below here, figure 3, part A and part B. In part A, line AB is parallel to line CD, and in part B, line EF is parallel to line GH. All right. So we're done with that. Let's look at other aspects. Now we want to look at symbolisms. That is, look here now. We want to look at symbolisms used in geometry. Some symbolisms used in geometry. Now, what are the symbols that, or the notation that are applied in geometry? Now, if we write capital AB, by capital AB, we mean a straight line that passes through the points A and B. So the letter A and B here stand for points. All right. So if we write them together, AB, this notation stands for a line that passes through, a straight line that passes through the points A and B. Now, a straight line does not have a definite length. If it does not have an ending, it does not have a beginning, it extends indefinitely. So nobody can draw a straight line in effect. Since we draw our line segment, we can draw straight line segments. All the lines we've drawn so far, they are all straight line segments. But practically speaking, we cannot draw a straight line. All right, practically speaking. So because it extends in either direction. So, but it passes through 2 points A and B. So in other words, 2 points A, B determine a straight line on the plane. So when we write capital letter AB, in this, that is uppercase AB, in this case we mean a straight line. That symbol stands for a straight line. So that is for that. Now number 2, we have the line segment, and this is the symbol for it. Look at it here. Can you see that? There's a kind of arrow above the notation AB. So in this notation you are seeing here denotes a straight line segment. A straight line segment is part of a straight line. All right. So the straight line segments between the points A and B. So this symbol here denotes the straight line segments between the points. Now distinguish carefully between the definition of a straight line segment and a straight line. You know, I said a straight line passes through the points A and B, but this one is between the points A and B. There's a marked difference. All right. Now to show that the points A and B are line segments, instead of writing A as a point and B as a point, we can also write them in the form of a line segment as line AA, as shown here. Can you see that? Look at it. So when we write line AA, we mean a point, the point A. But in this case, we are looking at a point as a segment, a part of a straight line. All right. So we have this as a point. Also, this can also denote a point, and this can denote a point. Can you see that? Now, number 3 notation is the modulus, or the length of a straight line. The length of a straight line segment. Please take note, we cannot determine the length of a straight line, because a straight line extends indefinitely. But for sure, we can determine the length of a straight line segment. Now, this notation is for the length or the modulus of a straight line segment, and it can be regarded as the distance between the points A and B. This notation you see here. Can you see that? All right. The length of line AB, that is line segment AB, the length of this is denoted by this symbol you see here. So whenever you see me write this symbol, I mean the length of this line segments. All right. Now, because it is a length, it is a positive, it's a non-negative, or it's a non-negative real number. You can consider it as a non-negative. When we say non-negative real number, we mean real numbers that are not negative. Example of real number that is not negative is 0. 0 is a real number that is not negative, and 0 stands for the length of a point. Don't forget that we can conceive a point as a straight line segment. So if we conceive a point as a straight line segment, the length of a point can be taken as 0, all right, which is a non-negative real number. And we can also have lengths such as 4, 5, and so on. So in other words, this symbol you see here, which is a length of a straight line, is an element of the set of a non-negative real number. This symbol you see here stands for set of non-negative real numbers. All right. So we're done with that one. Let's look at another one. Then this notation here, I've already explained it in passing. Angle AOB. All right. It stands for angle AOB. And when naming angle using this notation, you should ensure that the vertex is at the middle point in the order of your naming. I said that earlier on. Don't forget that. Very, very important. In this notation, the length OA is the first side of the angle, and the length OB or BO is the second side of the angle, as illustrated above. While the point at the middle is the vertex, and this is how it should be done. You can call it angle AOB, or you can start with BOA, provided the vertex is at the middle. It does not matter whether you start with AOB or BOA. Anyone is accepted. But what is important and necessary is that the vertex should be at the middle in the order of your naming. All right. So we're done with that. Now, this notation you see here, this number 4, this notation you see here is used to show that the line segment AB is parallel to the line segment CD. So if you see me writing this notation, line segment AB, then I put this 2//. It's meant that the line segment AB is parallel to the line segment CD. So take note of that. Then also look at this notation you see here. We use this to denote the fact that the line segment AB is perpendicular to the line segment CD. That is, the line segment AB meets the line segment CD at right angles. So when you see me writing this, I mean the line segment AB is perpendicular to the line segment CD. We shall come across these symbolisms in subsequent discussion. All right. So it is good to familiarize yourself with them now. Get familiar with the concepts that are being defined, because they are very important for subsequent studies. So we're done with defining parallel. All right. We're done with terms, some symbolisms in geometry. So now let's go to some geometrical axioms. What are axioms again? You know, I told you earlier on that geometry is a study of properties of shape. And these properties can present themselves in various forms. In the form of a definition, which I have explained to you above, in the form of axioms, in the form of theorem, in the form of a lemma, in the form of a corollary. All these are the possible ways the properties can present themselves. So when you see me writing theorems, I'm actually talking about a property. That is, the property is presented in the form of a theorem. It can be presented in the form of an axiom, in the form of a definition. All these are all properties. So be ready to know a lot of properties, because when we talk about shape, there are a lot of properties you will know. In fact, theorems or properties are the foundations upon which geometry is built. So without properties or theorems, you don't expect geometry to exist. All right, so let's look at some geometrical axioms. We shall consider the following as geometrical axioms. Some mathematical literature may not consider them as axioms, and we therefore provide a proof for them. All right, but in this course of study, we are considering the following as axioms, because they are axioms, they are assumptions, and therefore they don't require proof. There's no proof. We have to assume that they are correct, and by them we will establish other important properties called theorems. All right. Now the first of the axioms we are looking at is the sum of adjacent angles on a straight line. I've already explained what is meant by adjacent angles in passing. Now I want to look at an axiom about them. The sum of adjacent angles on a straight line is 180. So in other words, if adjacent angles are on a straight line, the sum of these angles will be 180. For example, look at this. Look at this figure here, figure 4 below. You see that angle alpha, beta, lambda, theta, and phi, they are all adjacent angles. And because of that, the sum of these angles is 180 degrees. And we don't require proof because it is an axiom. It's an assumption that needs to be accepted so that we can by it establish other important facts. All right. So that is why we call it an axiom. So we are done with that one. That is number one axiom you should commit to memory. Please know these things very well because we shall use them to prove later that the sum of interior angles in a triangle is 180, and that is a theorem. We shall use this reasoning process to establish that fact. So be very sure that you get a clear understanding of what I'm explaining now. All right. So we are done with that. Let's go to number two. Number two, say when two straight lines intersect at a point O. When two straight lines intersect at a point O, this point of intersection is called a vertex. And because it is a vertex, the angles about these points are called vertical angle. That is vertical. Vertical in the sense that they are about the vertex. So we call them vertical angle. All right. Now, the angles that are opposites, there's a fact about vertical angle. If the vertical angle are opposite each other, then they will be equal in size. They will be equal in size. All right. For example, let me illustrate with this. You see this angle here? It's a vertical angle because it's about this point O. Why this one is a vertical angle? But they are opposites. Because they are opposites, they are equal in size. So it's a fact that vertically opposite angles are equal in size. So that should be taken into account. Very, very important. Vertically opposite angles are equal in size. Now also note that in this diagram we have adjacent angles also. For example, angle AOB. Angle AOB. Can you see that illustration? I mean this. Can you see this angle here? It's angle AOB. Angle AOB and angle BOD. That is this angle you see here, angle BOD. They are adjacent angle because they are next to each other and they have the same point. Now they lie on a straight line AD. Because of that, by axiom 1, it follows that their sum is 180 degrees. Similarly, angle BOD, that is this angle you see here, and angle DOC, this angle you see here, they are also adjacent angles. And not just that, they are on a straight line BC. Because of that, it follows from axiom 1 that the sum of these angles is 180 degrees. All right. So we're done with that explanation. So we go over to the other aspect. Number 3, you say giving any arbitrary points O. All right. That is giving any point O, any point at all. We can form or we can construct angle about that point. So any number of angles we construct, it is true that the sum of the angles about the point is 360 degrees. For example, look at this figure here below. So you see that there's a point O and there are angles constructed about the point O. Now it's a true thing and it should be accepted as an axiom that the sum of the angles about this point is 360 degrees. So this is a particular case, all right? And also this is also a particular case. In this case, we have only two angles about the point O. So it's a true thing that the sum of the angles about the point O is also 360 degrees. So please, if in the case you draw any value from this video we are doing now, do me the favor to like, comment, share, and also subscribe to get notified when other fascinating math videos are uploaded. All right, so let's continue our study. Now I want to look at what is called corresponding and alternate angles. Corresponding and alternate angles. Corresponding and alternate angles. The first one is corresponding angles. When we say corresponding angle, what is the meaning of that? I said these are angles that have the same position. So the word corresponding angles is in relation with position, all right? So these are angles that have the same position. So when you hear corresponding angle, that angles are corresponding, what should come into your mind is that they are having the same position. Is that clear? Now, the statements of corresponding and the statement of equality are different. The fact that angles are corresponding do not necessarily mean that they are equal. Angles can be corresponding, but they are not equal. So there's a condition for which corresponding angles will be equal. So once again, I said that angles that have the same position or orientation are called corresponding angles. You can see that in the figure below. All right. Now, if you observe this figure, you see that angle AEX that is marked by two signs. Look at it here. AEX is having the same position with this angle here. Can you not see that? So because of that reason, we say that angle AEX and angle CFE are corresponding angles. Also, look at this angle here. This angle you see here, angle AEF. Can you see that? And angle AF. Let me see what is here. Let me scroll up to see what is there. All right. Angle CFY. Can you see that? Angle CFY. So this angle you see here and this angle, they're having the same position. Because of that, we call them corresponding angle. Can you give me other pairs of corresponding angle? If you say this angle here, that is angle XEB and angle EFD. If you say this, you are absolutely correct because they have the same position. And also, if you say this here also, angle BEF and angle DFY, you are absolutely correct because they have the same position. So in summary, corresponding angles are angles that have the same position. That is what you should know. And note that if angles are corresponding, that does not necessarily mean they are equal. There is a condition for corresponding angles to be equal. It is one thing for angles to be corresponding, and it is another thing for angles to be equal. Right? They are different concepts entirely. There's a condition for which corresponding angles will be equal. We're coming to that. We shall see that later. Now, let's go to the next part of the work. Now, the next part, the B part, is alternate angles. Alternate, or we call it opposite angles. What are alternate angles? Alternate angles are angles that have opposite positions or orientation. All right. So when angles have opposite positions or orientation, we say that the angles are alternates. Let's go back to our figure again. Look at this figure. If you observe carefully, you see that this angle here, can you see this angle? That is angle AEF. Angle AEF is in the opposite position to this angle here. Can you see that? Look at this. Look at my description. Angle EFD. Can't you see that? That this angle you see here, this angle you see here is in opposite position to this angle you see here. So because of that reason, we call them alternate angles. Similarly, look at this angle here. This one you see here is also in opposite position to the one you see here. So because of that reason, we call them alternate. So in this case, we have only two pairs of alternate angles, all like corresponding angles. In corresponding angle, there are four pairs of corresponding angles. But in this scenario, in this situation, we have only two pairs of alternate angles. All right. So please take your time to really go through this video. Make sure you spend time with this particular part. This is the foundation. Every other thing we will do is subsequent course will depend on this. All right. So you should have a proper grasp of this basic explanation because we shall always make reference to this. This is the foundation. If you miss this foundation, you will miss it all in the other courses. So be very sure that you get a proper grasp of what is being discussed now. Now we are done with definition of alternate angles. So now the question will naturally arise in your heart: when do corresponding angles, that is, what is the condition for corresponding angles to be equal, and what is the condition for alternate angles to be equal? Once again, the fact that angles are alternate does not mean that they are equal. Take note of that. as in the case of corresponding, so it is in the alternate case. The fact that angles are alternate does not necessarily mean that they are equal in size. They are two different concepts. As students over the years, students have confused these two concepts. All right. So for you to equate corresponding angles, you must ensure that a certain condition is satisfied, which I want to explain now. The same thing goes for corresponding. Now we're not looking at conditions for the equality of corresponding and alternate angles. Conditions for the equality of corresponding and alternate angles. All right, let's look at that. You can, in your video, you can slow the audio so you can get what I'm saying clearly. It's worth it, because when you get this foundational course, every other will be very easy. Now look at from figure 7, that we are referring to figure 7 once again. Here's figure 7. Let's look at it. Look at figure 7 here. All right, because it cited figure 7. So from figure 7, here's it again. From figure 7, if the cutting lines AB and CD are parallel, look at this figure here. If you observe carefully, the cutting lines AB and CD, can you see that? They cut a line SY. The name of the line is called a transversal. You understand? This the line XY that is cut by the lines AB and CD is called a transversal. And if you observe this transversal, a portion of it is captured by the cutting lines AB and CD. The portion EF, can you see the portion EF? Look at it here. EF, can you see this EF? This portion EF. That portion is called the SY intercepts. We shall look at that in detail in this course. All right, that portion EF is called the SY intercepts. So what is an intercept? An intercept is a portion of a transversal, all right, that is captured by two other lines. So we call that an intercept. Now, when will corresponding angles be equal in size, and when will alternate angles be equal in size? They will be equal in size if the cutting lines AB and CD are parallel. And of course, you know, I've explained what is meant by parallel lines in passing. So that everything is done in step. That's why I said you should take time to really go through this elementary aspects of geometry. So if the cutting lines AB and CD are parallel, then we are sure that corresponding angles are equal in size and alternate angles are equal in size. Otherwise, we are not sure. So be very careful. Angles may be corresponding but not equal in size. Angles may be alternate but not equal in size. For them to be equal in size, the cutting lines such as AB and CD here must be, I said must, it's a necessity, must be parallel. All right, must be parallel. All right, so we're done with that. I've laid emphasis on that already, so I think we can move on. So that is all about a condition for equality of corresponding and alternate angles. Then here I said something. I said note, the fact that angles are corresponding or alternate does not necessarily mean, I made this part now. Can you see this part? Look at it over here. Take note of that. The fact that angles are corresponding or alternate does not necessarily imply equality. Yes, I said that before. But whenever corresponding angles are equal, then the cutting lines, as in figure 6 and 7, are parallel. What does this mean? If angles are corresponding, that does not guarantee that they are equal in size. But whenever corresponding angles are equal in size, there is a necessity. What is it? The cutting lines that form them must be parallel. So in other words, we can use the equality of corresponding angles to prove that two lines are parallel. So if you are told in a problem to prove that line AB is parallel to line CD, what you should do? You should strive to prove that corresponding angles are equal. If you can prove that, you have concluded that the lines are parallel. So we can use this fact to establish that corresponding angles are parallel. All right? So take note of that. The same thing goes for alternate angles. That is, if alternate angles are equal in size, then the cutting lines forming them must be parallel. and we can also use that fact to prove that two lines or more lines are parallel. So this fact should be carefully noted. This is a very important fact because we'll be solving problem whereby we'll be required to prove that line AB is parallel to line SY. How do we prove that? If we can locate the corresponding angles, locate the alternate angles, and not just that, prove that they are equal in size. If we can do that, we can conclude that the lines that form them are parallel. So this is a very useful tool in proving that two lines are parallel. Take note of that. And so we can use this property to establish that two lines are parallel, as I said before. That is, if we can show that corresponding or alternate angles are equal, then the cutting lines are parallel, and we can and we call, not can, this can here is supposed to be called, all right, and we call the SY intercept as a parallel intercept. We call it a parallel intercept, all right. Now I want to look at special intercept. Let's discuss on intercept. We'll be talking on intercept. What is intercept once again? In passing, we said intercept is the portion of a transversal that is cut off by two lines. Let's go back to that figure. Over here you see the line FE is the intercept, but in this case it's a parallel intercept because the lines are parallel in this case. In figure 7 here, the intercept here is EF also, but it is not a parallel intercept. All right, so this portion of the transversal that is cut off is regarded as an intercept. So we want to look at special intercepts. Now, if we have the y-axis and the x-axis and the line that cuts across the y-axis, then we can regard this y-axis you see here as a transversal. All right, can't you see that? That is a transversal. This y-axis you see here is a transversal because it cut across two lines. One is this line you see here, and the other is the x-axis. So we can regard this line and the x-axis as the cutting line. Why this line here can be conceived as the transversal. But the portion that is cut off by these lines, by the x-axis and this line, this portion here, we call this portion, what do we call it again? Can you remember? The y-intercept. All right, the y-intercept. So that portion is called the y-intercept. Why? Because it's a portion of the y-axis. As we called the above, the sy-intercept, the same way, this is also regarded as the y-intercept. Now look at a second version here, but this time around now the transversal is taken to be the x-axis. Can you see that here? This is the x-axis, that is the transversal. Now a portion of it is captured by the y-axis and this given line here. This portion is called the x-intercept because it's a portion of the transversal called the x-axis. So this is the x-intercept. So summarily, intercept is a portion of a transversal that is cut off by two other lines. All right, that is a line intercept. We have other kind of intercept. We have the plane intercept. We are dealing with line intercept here. So we're done with this particular explanation. Let's go further. Now I want to look at the last aspect of this video. This is the last aspect, very, very important. And I shall leave you to internalize what I've explained. You can play the video once, twice, and thrice for a proper grasp. Because if this foundation is well laid, as I've explained to you, you see that every other thing we do will be very easy. Because we shall be making referral to this particular video. Because it's a foundation of every other thing we're going to do. Now, theorems. In geometry, it is customary to carry out the proof of theorem. You know, I told you that a theorem can be proved, but we cannot prove an axiom. We prove the theorem by logical reasoning on definitions. Don't forget, definition is also a form of a property. By axioms, by previously proved theorem. Maybe if a theorem is previously proved, we can base on that to establish a given theorem. All right. So, but in geometry, there's a tradition, there's a custom in carrying out the proof of a theorem. That is not applicable to other branch of maths. This is only restricted to geometry, and it's restricted to carrying out the proof of theorem, not any other problem, just for theorem. Now, what is the tradition or the custom that is applied when carrying out a geometrical theorem? Number one, the following are necessary. Number one, there should be a statement of the theorem in words. It should be a statement of the theorem in words. All right, that should be, for example, the sum of interior angles in a triangle is 180. That is a statement of the theorem in words. Number 2, there should be a general diagram of the figure discussed in the theorem. Now, for example, the theorem I stated just now, the sum of the interior angles in a triangle is 180. What figure is talked about there? What figure is being discussed? It's a triangle. And when we say a triangle, the word a is an indefinite article. That means it can be any triangle. So we are proving this theorem for the general triangle. All right, it's a general case. So if you draw a figure, the diagram is a general diagram. That is, it represents all possible triangle. Can be scaling, can be obtuse angled triangle, and so on like that. So this number 2 step is that a general diagram of the figure that is discussed in the theorem, it should be labeled with suitable lettering. It should label, like if I draw a triangle now, I will label it as ABC. It should be labeled like that with suitable lettering. Number 3 step is by the lettering, that is, by the lettering you have given, a statement of what is given. All right. So now in a theorem, there's what is given to you and is found in the antecedents or hypothesis. Don't forget, I said a theorem is an implication. All right, and an implication has 2 parts: the antecedent and the hypothesis. All this I explained earlier on. All right, so what is given to you will be captured in the antecedent part of the theorem. For example, the sum of the interior angles in a triangle is 180. What is given to you in this statement? It's a triangle is given to you. That's what is given to you. All right, you are given a triangle. You are required to use that to establish that the sum of the interior angles, which I will explain later, is 180. Now, number 4 step of the tradition is this: a statement of what is to be proved. Now, you must give a statement of what is to be proved. For example, in the theorem, the sum of the interior angles in a triangle is 180. What are we to prove? We are to prove that the sum of interior angle is 180. That is what we are to prove. So you should give that. You should provide a statement for that. Don't worry. When we'll be looking at a particular example, all these steps will be displayed in the example. All right. So just familiarize yourself with them. Number 5, any construction if necessary. Now, sometimes you cannot carry out the proof of a theorem unless you add construction to it. But the question now is, how do we know which construction to be added? That is based on what you've learned before. Now, all what we've learned before has given us good momentum to establish that the sum of the interior angles in a triangle is 180. I will display that in our next video. All right. So all what we've learned before now, like for example, we've learned about corresponding angles, about parallel lines. All these things we've learned so far, adjacent angles. All these things will aid us to prove that the sum of the interior angles in a triangle is 180. And when I will construct in the light of what we've considered previously. Hence, I said what we are doing now, take it very serious, because every other thing we're going to consider will be based on them. So make sure you spend time with this video. All right. Oh, my battery is almost gone. Now we're done with that one. Any construction, if necessary, so that it is necessary for construction, so that the theorem will be provable. But some other time it is not necessary. What is given to you in the antecedent is sufficient to carry out the proof. All this we shall see later. Then the last stage of the proof, and this should be in the form of a reasoned argument. All right, it should be in the form of a reasoned argument. Now, in the proof process, reasons for statements should be within pari tenses. Reason for statements you make should be within pari tenses. So we've come to the close of this particular video. Thank you very much for your time. I really appreciate you all. Make sure you like, share, comments on the video. Also subscribe so that you'll be notified when a fascinating mathematics video is produced. So thank you very much. I wait for to see you in the comment section.